David Kaiser's How the Hippies Saved Physics is a fun and fascinating deep dive into an often overlooked chapter of modern science. The unlikely intersection of quantum mechanics, counterculture, and the free-spirited intellectualism of the 1970s. And yes, there's plenty of acid-induced experiences. It tells the story of the fundamental Fysiks Group, a band of rebellious physicists who, amid the decline of fundamental physics funding, explored the mysteries of quantum mechanics with a truly open mind, trying to see if they could bridge the gap between science and mysticism, and finding alternative ways to come up with funding on their own. The book starts with the backdrop of the post-World War II physics boom, which had seen an influx of government funding into applied physics, particularly for military and industrial applications. However, by the end of the 60s into the 70s, theoretical physics, especially fundamental physics, those parts not directly linked to weapons research, was struggling for support. This was the environment in which the fundamental Fysiks Group arose, composed of young physicists and thinkers unable to find work, disillusioned by the rigid, utilitarian approach of mainstream physics, who refused to just shut up and calculate. Kaiser introduces us to key members of the group, including Jack Sarfati, Fred Allen Wolfe, Nick Herbert, and Elizabeth Rauscher. These individuals met in coffee shops, communes, and unconventional academic settings in Berkeley, California, discussing the philosophical and metaphysical implications of quantum mechanics. They drew inspiration not just from established physics, but also from Eastern mysticism, Buddhism, parapsychology, and New Age thought. The book details how the fundamental Fysiks Group challenged the dominant shut-up-and-calculate attitude of physicists like Richard Feynman, who dismissed the deep philosophical questions of quantum mechanics in favor of pragmatic applications. The hippie physicists, on the other hand, were deeply concerned with concepts like quantum entanglement, non-locality, and the role of consciousness in physics. Problems we are still working on today. A lot of the science is around John Bell, whose Bell's theorem laid the groundwork for experimental tests of quantum entanglement. The members of the fundamental Fysiks Group were among the first to recognize the significance of Bell's work, even when much of the mainstream physics community dismissed it as untestable or irrelevant. They saw Bell's theorem as proof that quantum mechanics allowed for spooky action at a distance, an idea that would later be experimentally confirmed and become foundational in modern quantum information science and computing. Jack Sarfati, for instance, was convinced that quantum mechanics could explain psychic phenomena, telepathy, and even time travel. Sarfati's ideas were often too far out for even his fellow unconventional physicists, but his enthusiasm helped keep the discussion of quantum weirdness alive during a time when many physicists preferred to ignore such implications. Nick Herbert, another central figure, wrote Quantum Reality, a book that popularized many of the group's ideas and remains influential today. Herbert explored the idea that quantum mechanics could be linked to human consciousness, a notion that fascinated the New Age movement. The fundamental Fysiks Group became involved with the Salem Institute, a hub of countercultural intellectualism where physicists, mystics, and philosophers mingled freely. While many of their wilder ideas did not gain traction, their interest in Bell's theorem and quantum entanglement laid the groundwork for what would eventually become quantum information science. The book argues convincingly that their persistence in studying quantum weirdness played a role in the rise of quantum cryptography, quantum teleportation, and even quantum computing. For example, the experiments of a land aspect in the 1980s, which confirmed the reality of quantum entanglement, might never have been pursued if not for the enthusiasm of the fundamental Fysiks Group and their insistence that these ideas were worth exploring. Today, companies like Google and IBM invest heavily in quantum computing, an industry that owes part of its origins to the hippie physicists who refuse to let these questions be ignored. Some readers may find the group's fascination with mysticism and the paranormal frustrating. I found they spent too much time on Uri Geller and his bending spoons and other parlor tricks, but enjoyed their free love communes and willingness to take any pill or powder to fully immerse whatever the experience was supposed to be. Kaiser does not argue that their wildest ideas were necessarily correct. Instead, He shows how their willingness to ask unorthodox questions helped keep interest in foundational issues alive during a time when mainstream physics had largely moved on. The book is both an entertaining read and an important reminder that scientific progress often requires open-mindedness, even toward ideas that seem outlandish at first.